Unilever is a consumer goods company which sells products in over 190 countries across the world. It makes beauty, personal and home care products, tea, ice cream and other foods. And its sales of over 400 brands across the globe mean that it can use those as a force for change, a force for good, and also to fulfill its purpose of making sustainable living commonplace. Since the 1980s, Unilever has looked to eliminate animal testing. To do so, it has invested considerably in the development and application of non-animal approaches. The work we have done internally has been led by our Safety and Environmental Assurance team, SEAC.
In SEAC, we work a lot on the safety of new ingredients going into Unilever brands to make sure that they're safe when our consumers use them. I think the important thing about the way we're approaching safety is trying to understand how an ingredient might interact with human biology. And to do that, we use a lot of different approaches, ranging from computer modelling to cell culture in complex areas and some quite novel mathematics. Over the years, we've worked a lot on some of what you call topical toxicity, so effects on the eye and the skin. And one of the biggest challenges that we're working on now is what happens if a chemical penetrates through the skin and into your blood system, and actually understanding the systemic effects of a chemical.
Next generation risk assessment, or NGRA, is an exposure-led, hypothesis-driven risk assessment. The NGRA concept is really a development of the ideas of the National Research Council's book, Toxicity Testing for the 21st Century, Vision and Strategy. And what we're really trying to do with an NGRA is give practical value to the concepts that were in that book. So one of the key concepts in an NGRA is that we're not trying to predict apical endpoints that we would normally measure in experimental animals. What we're trying to do is use these in vitro tools in a broad range of human cells and tissues to characterize that bioactivity, which is really a capture of the molecular initiating events that a given chemical can have. And we're comparing the levels of that bioactivity with the bioavailability of that chemical. That is to say, its internal exposure.
The NGRA framework starts with exposure. Everything that we do is exposure-led, and the consumer is at the heart of everything that we do. So we think about how the consumer uses the product, and we think about how much of those different ingredients which are in that product will be getting into the consumer system. And so we start with consumer habits data, and then we build on there. And we think about internal exposure using PBK modelling.
PBK is a core principle we need to start off with when we're doing risk assessment. It allows us to get a good understanding of how much of the chemical is going to be in the systemic circulation. So when we're carrying out PBK modelling, there's lots of areas uncertainty can come into this. So we've got the variability in the different people, the different consumers, so their height, their weight. These sort of things will affect the outcome of the model. To do this, we'll sort of generate a virtual population. We'll create different individuals and run the model a lot of times, and this will allow us to get a distribution of the possible systemic concentrations that we'll see across a consumer population.
So when we're looking at doing next generation risk assessments, the first point is always to collate as much information as we can. And we can get a lot from the structure itself, so we use these QSARs, the quantitative structure activity relationships, and we use a lot of historical data that's been gathered, so on other chemicals, not necessarily the one we're looking at. And they will have similar fragments, similar structures, and we can say, okay, when we look at this, how did that affect a human? What kind of effects did it produce in a person when they used it? And once we have that, it builds up a database of alerts, and these alerts help us form a hypothesis and work through the rest of the risk assessment. So things like you get alert for DNA binding.
So for DNA binding, we would immediately go and look for something such as genotoxicity. So we could run assays such as the Ames test or the IVM, which is the in vitro micronucleus test, or we could use an assay such as the Tox Tracker assay. And the Tox Tracker assay is a 6 GFP reporter cell line based assay, and it looks at the mechanisms behind genotoxicity and builds up a picture of how exactly a chemical could be causing genotoxicity.
The kinds of bioactivity data that we use are really important because they need to be broad enough to give us enough coverage to be happy that we can make a confident safety decision. And really they're broken down into three groups. We have high throughput transcriptomic data to give us a breadth of biological coverage of gene interactions.
Transcriptomics for us is a very useful assay because it provides something that other assays aren't providing. It gives us a very broad, unbiased view of what biological activity might be occurring. In essence, it's addressing the question of what else could be happening when this chemical interacts with the biological system that we cannot currently predict up front from the structure. And I think the primary assumption that we are driving here when we are looking at a protective goal is that assumption that actually we would not see adversity unless there was a gene expression change is the key assumption that underpins this. And that is what we're currently testing.
We have safety screen data, which enables us to look at receptor interactions so that we can be confident we're not perturbing anything there.
The safety screen or pharmacological screen is an assembly of assays that include a broad range of targets with well-established links with human in vivo adverse effects. These targets they include GPCR receptors, nuclear receptors, ion channels, transporters, and intracellular enzymes. And the safety screen is conducted in two phases. In the first phase, we measure the bioactivity of the chemical using constant concentration of the chemical across all the assays. In the second phase, only these assays in which we see certain inhibition or activation of a chemical are progressed. And usually in the second phase, we use more relevant functional cellular assays from which we can derive the IC50 and later we can use it for point of departure.
And finally, we think about the cell stress panel, because cellular stress is a really important way where ingredients could cause adverse effects in consumers.
So many of the compounds that are relevant to consumer safety will act through non-specific modes of toxicity leading to cellular stress. For that reason, it's important to develop appropriate assays for which you can identify stress pathways that might be of concern. So the cell stress panel is a large set of assays consisting of 36 different biomarkers that cover 7 different stress pathways along with mitochondrial toxicity and various cell health effects. So for each of those biomarkers, you measure the response to your chemical, and from that you can determine which of those stress pathways are actually being affected by your chemical. Once you know that, then you can do more detailed concentration response assays to then calculate points of departure, which you can then use to inform your safety risk assessment.
We put all that data together on an exposure activity plot so that we can understand what sort of margin of safety we're talking about and whether we can make a confident safety decision or not.
Essentially, if this margin of safety is large enough, then we think this is going to be safe for our consumers. Recent research has shown that new approach methodologies are more conservative than animal studies. Therefore, we think deriving point of departures from a range of in vitro tools, we are going to be more conservative in our safety decisions.
It's really important to us that any new approach that we apply in safety decision making is going to keep our consumers safe. So the analyses that we've been doing and others like the EPA really serve to make sure that any decisions that we take are going to be conservative and are going to be protective for our consumers.
This is a really big global effort to find ways of assuring safety without animal testing. Our scientists work with scientists around the globe, all working to find the best new approaches for assuring safety. And that also includes working with some regulators, with NGOs, and with trade associations in various parts of the world.
I think it's important to recognise that an NGRA is not a done deal, so to speak. We know there are certain shortcomings associated with this approach. Things like understanding the biological coverage with the different in vitro tools that we've got, the temporal aspects associated with those treatments, and are we getting 100% prediction with our PBK methodologies. But we are working with a number of different groups around the world, many different partnerships to address these shortcomings. And we know we can see the light at the end of the tunnel. These are the ways that we are going to do our risk assessments in the future.